So it's planning to continue this afternoon lecture with Eugenia. When I was organizing this conference, I wanted to spread out, to move outside of our mind common people. So I looked and I knew that from Guillermo I could find people interested in similar problems, similar areas, but that we don't have contact, specifically because we are too far away. So for the ones that know, South America is gigantic, and we only speak the same language, but sometimes people in the US ask, "No, so you go to Buenos Aires?" But no, it's like 8 hours, costs a lot of money. So we're far away from each other, and so it's difficult for us. So I'm very glad that Eugenia accepted the invitation. She's coming from Uruguay, from Universidad República. There was a student of Guillermo Cortiñas, who was a renowned as a non-commuting geometry topologist in Buenos Aires. So, Eugenia, thank you.
Thank you very much for the invitation. I'm very happy to be here and to speak about this work. I have to say that this is my first conference in the United States. Thank you for the opportunity to be here. Thank you. And I'm going to talk about one recent work with Emmanuel, who also is a student of Willy. Is from Argentina. Then what we do in the work is a relation between the Davis-Lück homology with coefficients in the homotopy, in the Weibel's homotopy K-theory, and with equivariant algebraic KK theory. Then I'm going to explain what is that equivariant algebraic KK theory, and I'm going to say something about the Davis-Lück homology also. And this connection allows us to express the left-hand side of the assembly map for the KH-isomorphism conjecture in terms of equivariant algebraic KK groups. Then this is the whole story. Then I'm going to go into this. Then first, I'm going to introduce algebraic KK theory, which was introduced by Willy Cortiñas and Andreas Thom, in order to show that some method from K-theory of operator algebras can be applied in completely algebraic setting. Then L will denote a commutative ring with unit, and this is going to be the category of algebras over this ring. Then what we have is a dictionary between Kasparov KK theory and algebraic KK theory. KK theory is a bivariant K theory. Then we have, in the case of Kasparov KK theory, we have two separable algebras. Then a KK group is defined for each pair of sister algebras. These groups are the home set of a category KK, which is a Jangulate category, and there is a functor from the category of sister algebras into this form. And this functor satisfies some properties in the context of Kasparov KK theory, and in the algebraic context also satisfies some properties. Then the first one is the stabilization with respect to compared operators. Here, then in this category, this algebra and this algebra, which is the stabilized algebra, are equal in KK. In the algebraic setting, what we have, we identify an algebra A with the matrix algebra. We also have homotopy invariance. In the Kasparov KK theory, we have continuous homotopy invariance. In this case, as we are in an algebraic context completely, what we have is a polynomial homotopy invariant. That means that this sister algebra, the continuous function from the interval to an algebra B, is identified with this sister algebra, and in the algebraic setting, we have this polynomial identified with this one. Okay, these functions are universal for these properties. This was studied by Hickson, and this was proved by Cortines and Tom. And in here, in this case, Kasparov KK theory is a common generalization of topological K theory and K homology. Then, if we put the sister algebra, the trivial sister algebra, the complex numbers here, we recover the topological K theory of this sister algebra. If we switch, what we have here is the K homology. In an algebraic context, if we put the base ring here, in the first input, what we have is the Weibel K homotopy groups of A. This is a this group sometimes coincides with algebraic A groups in the case that A is Noetherian on Red. But it's the theory that satisfies this functorial property. Then, some time ago, I introduced an equivariant version of this algebraic K theory, and we can continue with the dictionary. Then we obtain a category KKG instead of sister algebras. We have G sister algebras. We have an action of G on sister algebras. Here, G would be a topological group, but for the rest of the talk, it's going to be this way. In the case of in the algebraic setting, always discrete. Then the stabilization with respect to compact operators in the algebraic setting, we have matrices where the index of matrices are indexed by G, and G also acts there. Then and this G algebra is identified with this one. G here acts on A and on G. We also have homotopy invariants. And if we put the trivial algebra here, if G is compact, what we have is the K theory of the cross product, reduced cross product of G into A. And in the algebraic setting, if G is finite and the order of G is invertible, then what we have is the K homotopy group of the cross product. Then our work with Emmanuel tried to continue this dictionary in the sense that there is a conjecture called Van Con conjecture, which wants to compute these groups. And there is a formulation of this conjecture using KKG theory. Then in the algebraic setting, we want to make something similar with equivariant KKG. Then what the conjecture that we have and which want to compute KH is the KH-isomorphism conjecture. What we have done is to formulate the left-hand side of the conjecture of the assembly map. The assembly map is not so, it's open. Then, okay, this is a motivation. Then, the thing that we need in algebraic theory is these two adjointness theorems which relate KKG groups with KK in the case that G is finite and the order of the group is invertible, then we have an isomorphism here. This is B is an algebra, BT is a G algebra with the trivial action, and this is the cross product. And if we have a subgroup of G, then we can take induction algebra from an H algebra and obtain a G algebra and a reduction. And we have also an adjointness theorems between this thing. Then another ingredient that we have is a spectra representing algebraic KK theory, which was introduced by Emmanuel and Arcusha. Then what we consider is a spectrum for each pair of algebras. We consider a spectrum such that the stable homotopy groups of this spectrum are the KK groups. And the non-equivariant and the equivariant set. Okay. I need something to continue the formulation. I have to talk about algebra of polynomial function on a simplicial set, which is denoted by L up to X. Then, if we have we consider this simplicial algebra, and then if we have a simplicial set, we can consider the polynomial function on X as the simplicial map from X to this simplicial algebra. And we take those with finite support. Then, why that here there is a functoriality problem or satchel that we need to deal. Then we are going to consider this ring, which is a ring associated to a linear category. Then, if we have a G algebra as a group, then we consider this category, whose objects are the elements of G mod H, and the morphism are these L mod U. And we consider the product here given by the cross product rule. Then this is a linear category. And if you have a linear category, we can consider an algebra, which consists in to take the direct sums of home sets of the category, and with the multiplication given by this rule. Then if you have two things, if they can be composed, you compose it, and if not, take to the garbage and take 0. This ring is not completely functorial because we cannot, there is no functor from L linear categories to algebra, but we can take this one, consider the tensor product of this ring, and then we can have a function from the linear categories to the algebra. And then we need this ring associated to this linear category. Yeah. Well, the Davis-Lück homology is constructed taking a function from the orbit category to the category of spectra. Then if we have a group, we consider the orbit category. And a functor from this orbit category to the category of spectra can be used to construct an homology in the G-simplicial set. This is the way which is defined. And if you have a family of subgroups of G, we can consider a G-simplicial set, which is a module of a classifying space respect with F. That means that this is a G-simplicial set that the fixed part of this space is contractible if H belongs to F and is empty if not. For example, if F is the trivial group, then it's the classical EG. Then we take the projection of this set to one point, and we apply this homology theory to this projection, and then we have a map. This is the assembly map of the conjecture associated to this triple, GFE. And we say that the isomorphism conjecture is true for this triple if this map of spectra is a weak equivalent. Then the KH-isomorphism conjecture is formulated in this context. Then we have a group, any group. We have the family of finite subgroups of G. And the functor from the orbit category to the spectra is using the spectrum representing algebraic KK. And using the ring that I have defined before. Then, if we take homotopy groups of this spectra here, we obtain the KK groups. And these KK groups coincide with the homotopy K theory of the crossport. Then a group satisfies the KH isomorphism conjecture if this assembly map is a weak equivalence. Then our main theorem expressed express this this spectra in terms of the spectra related with algebraic KK theory. This is our main theory. Then this involves a little some technicalities. I am going to try to give you an idea of technicalities. Then what we have what we do is to use adjointness theorems and some homotopy theory here. Then we have two steps in the proof. The first one is take another spectrum. This is a functor, it's well defined, and this is also a functor, it's well defined, but only when H is finite. Then now we are going to work only with G finite, G fine complex. The orbits are G mod H with H finite. Then the first step is to replace the coefficients in this functor with coefficients in this functor. Then and see that the homology coincides. And then we prove that the homology with coefficient in this functor coincides with algebraic K. Yes, the two parts. Then the first one, we take a morphism of spectra from here. This is a spectrum. From the here we only consider G complexes, because if we, I have to say something. F is a functor from or G to spectra. Then this functor give a GF complexes homology. Only here, and then F only allows us to work with this complex. Then, okay, we define this map of spectra, which are natural in I, Y, and if Y is G mod H, this is a weak equivalence. And then we extend to bigger complexes, taking another natural weak equivalence spectrum. Then we prove that these maps are weak equivalence in some steps. First, by construction, we have that this is true, because this is here, and then we continue by steps. Then if we take a simplicial set, which is only one cell of dimension n, we can use this result because we have homotopy invariance in the homology and in KK. Here, if we have a union of some cells, we use this step because homology and KK behaves well with sums. And if we take the homology of this, is the sum of each cell, and in KK there is something similar. And the last one is in the homology part, we have Mayer vectoris, and in KK we have another property similar. Then KK, we don't have whole Mayer vectoris, but we have a property very similar. Okay, then we have this homology in terms of these groups. Then the hardest part of this story is this theorem. This is the most important technical part, which is a construction of a zigzag between these two O spectra. What is a zigzag? Is something like that. We can have arrows at the back, but this means that this is a weak equivalent. Each arrow like this has to be a weak equivalent. Then we construct a zigzag between these two orogeny spectra, and then we have that the homology is the same. Then, if we combine the two adjointness theorems, we have this isomorphism, which is at the level of groups. But if you see this isomorphism, which is at the level of group, also holds at the level of spectra. But here we cannot take this spectrum because here we don't have functoriality. Then we cannot say anything about this morphism. And this morphism, we can say about the composition, which is an isomorphism. Then we have this adjunction, but we don't have naturality.
This is some like restriction induction.
Here, yeah, this is induction restriction, and this is linear. Is the combination of two adjointness theorems. Then we want to lift this thing to an a natural isomorphism of weak to a weak equivalence of the spectrum. Then what we start with a primitive zigzag at the level of groups. Then here we have these groups, which are the homotopy groups of the beginning. We take these functors, this functor, then we pass to equivariant KK. This is a G. We have an action, the regular action of this G set provides an action of G. Then here we have a morphism, an algebra morphism. And this one is the co-unit of that adjunction. I have problem with this word, adjunct. Then what we have here is a zigzag of groups, and we want to lift this zigzag in a natural way. But we have two problems here. One problem is that this has three inputs of G mod H. Then we need these things to be a functor from G mod H to spectra, and we have three things here. Then we have to solve understand how to consider these two spectra as a functor from G mod H, and then have a zigzag with it, which is natural from G mod H. Then let's take let's change a little bit the notation. Then consider all the orbit category with finite subgroups. And okay, let's consider R, S, and T to the letters of the zigzag. Then, okay, the problems are to consider this as a function, and then what happened with natural. Then what we have done is, okay, these things with three things are, we consider this one with fixed T as a B functor on this category, the orbit category. A bifunctor to spectrum. Then we take this thing with the S inside of the R and with the S outside of the R. Then we have this zigzag, who we have to massage to have a natural zigzag of spectrum. Then these maps has a property which allow us to consider coends there here. Then these maps satisfy such that if we have an F, here, sorry, we have F from alpha to beta, then we have this map and this map, and then this square commute with these maps. Then we can consider the coend, and we have a map here from this to this, such that this morphism is natural in an element of 4. By a reason that is coming later, we have to take the slice category over T. It's a subcategory, it's like a slice category. Are the pairs that, and the map is an element of, and this is there is a map from S to T. Then we need this map to define one morphism later. But that's why we consider the slice category, but the forgetful functor allow us to see some bifunctor from O to spectra into bifunctor to slice category to spectra. Then, by this way, what we have is here, this thing now is a spectrum, which only depends on T, because the other two T's disappear. And we have here a morphism, which is natural on T. Then, okay, let's do the same here. We take the coend, but if we take the coend here, we lose the condition of weak equivalence here. Then what we want to do is take the homotopy coend in order to keep this weak equivalence. Then, in order to put some structure here to consider homotopy coends, we take some results of Lee. Then if we have a model category, closed model category, and a small category, we can consider two model structures on the functors from gamma to C. Taking point-wise, object-wise configuration and weak equivalence, or fibration and weak equivalence, and not always exists this structure, but if the category is combinatorial, then we have this structure. Then we have the spectra with simplicial sets are a combinatorial category. Then we can derive this is the homotopy coen, which is a left Quillen functor. Then the weak equivalence is we can keep the weak equivalence there. Then what we have here now is a map which is also a weak equivalence. And I'm not going to continue with the details of this zigzag here, but it's all this everything is written in the paper. But here we need to define a morphism here, and for this we need the morphism here. This allows us to construct this map, and this map is used to define this zigzag. Then this is a zigzag of spectra, which is natural in T. And by this, we finish our proof. Then some comments about Maucon conjecture. I don't know if someone is some question. Then some comments about Maucon conjecture. Then there is two assembly maps which define conjecture. First one, or the second one, it's not the original one, but I put it first, is the assembly map of Davis-Lück, which take the family of finite subgroups of G, and they use a spectrum using topological K theory. And the original Maucon conjectures assembly map with coefficient, because we have a G algebra B. We know that this conjecture is not true for all B. Then the assembly map is constructed like as follows. For each proper G space and G compact, there exists an idempotent element here, such that if we take descent map and recompose with this idempotent element, then this is used to define the assembly map of Maucon conjecture. And here we have the left-hand side of these two maps are the same, but at the left, we have an equivariant homology, and here we have Kasparov KK theory. And these two maps were identified recently in full details. All the people say, okay, are the same, but the full details were identified recently, and with different techniques that we use. We use different techniques than they. And I would like to say a little bit about this identification. Then Kranz identified these two assembly maps. This is the assembly map and this is the assembly map using the Richard Ness and Ralph Meyer approach. They expressed the assembly map of Baum-Kohn conjecture as a localization map. Then here there is also a D here, and this is an equivalence. This is an equivalence. Then they say, okay, this assembly map is equivalent to this one. Kranz used this picture and identify also this part of the square. I say, okay, this assembly map is identified with this, and this assembly map is identified with this, then these two are in black. And also, Ulrich Bunke, Engel, and Land has a paper which identified these two assembly maps using a structure of infinity category on Kasparov KK and using coarse geometry. Then, in our case, if we want if we want to construct an assembly map using an idempotent here, what we have done is taking idempotence when X is G mod H. Then if H is finite and you choose a class here, there is an idempotent, which depends on the class that you take, but the class in KK does not depend. This is another. And this thing, that's why at this level we can define some map at the KK group, but not at the level of spectrum. And our zigzag here is compatible with this assembly map. This is the Davis-Lück assembly map, and this all of this commute. An open question that we are trying to go a little bit further is what happens if we have a simplicial set bigger? If we can, the question that we have is if we can space these elements and define something here. In order what? In order to have an assembly map from KK to KH. Then I have some reference. Everything is written there. And okay.